So, good evening, everyone. Sorry, just trying to get everyone's attention. Good evening. Thank you for making your time for the seminar today. It's going to be Dougall who is going to do most of the talking, but I thought I can take the opportunity to introduce EPECentre and Dougall for those who are new to us. So we have about 12 individuals online. 10. So you may need to stand here and talk so you hear the speaker. So this week. So just to give a very brief background about EPECentre, I'm Radhnya Mukhedkar. I've joined EPECentre in November 2018 as the director. And the EPECentre is a part of the College of Engineering at University of Canterbury. And we primarily are involved in research and innovation activities and education and outreach, with a very strong linkage between the industry and academia. So in terms of research and innovation, some of the major projects that we have undertaken and are also ongoing right now include power quality, Dougall heating project, and green grid. Power quality and green grid focusing on the electricity infrastructure, and Dougall heating is a unique application for electricity in the forestry industry. In terms of education and outreach, we undertake a number of activities in partnership with the ECE. We support events for high school students. When I joined, I think that was the first time I was able to participate along with Dougall for the New Zealand Young Physicists tournament, and it was quite enjoyable interaction with students. We have typically year 12 and 13 students visiting the laboratory facilities in July. In January, we were undertaking some miniature electric vehicle racing for the Women's in Engineering workshop that was held over a week. We are supporting students, undergraduate and postgraduate, with scholarships. Since 2003, we have had around 190 scholarships that were awarded, and at present we have 37 scholars. Also, we are supporting other events for the UC students, which includes field trips. That's really popular, and it is supported by our industry members as well as certain manufacturing industry companies. It alternates between the North Island and South Island, and this year we had the visits were organized for the North Island. Typically, it takes place in April. We also support a career day for our industry members, and it's going to be on 30th of July this year. There is a lot of interaction with the industry and also through research activities. We support students for their summer projects. Typically students from second year and third year. There is also an opportunity to make research presentations to the EEA conference, which is offered by EPECentre. As Isabel identifies the multiple tools, EPECentre was established in 2002, and at present we have 22 industry members. I would like to introduce Dougall. He has accomplished his PhD in 2016 with the EPECentre through the Green Grid project, and his subject was related to the disbursement of wind parks and the stability of the electricity network. Today he actually has a significant amount of experience, 15 years, primarily as a wind electricity engineer. And today we have him with us, and he will be talking through there is a potential for pump hydro storage for New Zealand.
Okay, so as Radnya said, I've worked as a wind energy engineer, and potentially that is going to lead us towards a problem with our power system in keeping and maintaining balance as we integrate more in order to satisfy our need for electricity to power our carbon zero economy and all of the electric vehicles and everything we're going to bring into our grid. So the relevance of pump hydro becomes more important. So what are we talking about in terms of the electricity industry is maintaining balance in our power system and keeping it rolling. But we're going to have this equation we've got to meet where we have a carbon zero economy, of course the proposal introduced to Parliament today, which means we're also going to have a great deal of electrification from car vehicles and other industrial loads, and we've got to meet this electricity demand using a combination of our existing generation portfolio of hydro, geothermal, and a little bit of wind. And to that, we're probably going to add quite a lot more geothermal, some solar power, some wind power. But we are going to have to do some balancing as well, because we're probably not going to be able to get enough demand-side management to be able to shift our loads around to keep that power system balanced. In terms of the requirements that we will need, if we're just looking at achieving a 100% renewable grid, then Ian Mason here at Canterbury did some work calculating that in 2013 we would need 1.5 gigawatts of additional generation capacity with 368 gigawatt hours of energy supplied per year, or even bigger numbers if you look at 2050 projections of Transpower in Te Maui Hiko, we might need 5 gigawatts of extra online capacity. However, the balancing of this power system has to be done. These are temporal spans. We need it to be balanced daily during synoptic, so passage of weather storms. That varies with the wind availability, and also, of course, in New Zealand we have dry year problems, so we've got a seasonal storage issue as well. In terms of the stability of the system, we've got inertia in the system, and that might be decreased as we decrease our amount of synchronous generation plant when we decommission our fossil fuel power stations. And wind may be able to provide some through synthetic inertia, but there's certainly going to be a change in system characteristics, and our reserve requirements will have to be changed to meet that. We've also got to always consider within our power system hopefully the inevitable need for black start capability, which requires synchronous generators. And this balancing issue is already being, to a point, addressed looked at. It's becoming topical within the electricity industry. Companies like Mercury are installing batteries which are grid connected. So they've connected a 1 megawatt, 2 megawatt hour battery at Southdown. However, there are some issues around batteries. Their longevity, they're not shown to have a great lifespan, potentially only 15 years, and the capacity and availability of lithium and the carbon intensity, of course, is problematic as well. So, but we can have a look, and I've got a couple of cartoons here. I think some people have probably seen these before. The elephant in the room in terms of storage is, of course, pump hydro, but that same elephant is synonymous with being a white elephant, particularly in Australia, where it's not received a great deal of good coverage up to date, although now it is becoming more important and there are pump hydro plants being constructed across the Tasman. So we can look at whether or not we're talking about an elephant or mouse using some analysis that I've just picked out of the literature. Top left there is the levelised cost, and pump hydro is by far the best in terms of its economic performance, primarily really because of its long lifespan, its longevity. Once you've built a pump hydro scheme, it really doesn't require a great deal to maintain it. and that's reflected in the energy stored and invested, where pump hydro compared to lithium ion, the P2H2P is the hydrogen, which of course is receiving a lot of attention in New Zealand at the moment. This is all based on existing technologies, of course. I have used references which are recent within the last couple of years, but still these figures will change. I also have included vanadium flow redox batteries, which are being investigated and developed here at the university as well, and have great potential for further development, and of course these figures will change. But nonetheless, in terms of all of the metrics I've looked at, pump hydro really does stand out above, head and shoulders above the rest. And it also comprises over 95% of active storage worldwide, so I actually mean active storage that's not passive storage as we have in our hydro reservoirs. This is where we're actually actively using energy to store energy. However, it does have some criteria. It's economic at scale. It really requires large plant, and worldwide the mean capacity is about over 300 megawatts, and really a lot of plants are in the gigawatt scale, and it does benefit from economies of scale. However, it is capable. You can use synchronous machines or asynchronous machines. It's very flexible in its construction, and as I said, it has longevity and resilience, and it can be integrated into the power system relatively easily. And in terms of New Zealand's perspective, I've put here economically circular. Most of the economic activity that would be undertaken to construct a pump hydro plant would be undertaken within our own country. All the civil works, all the design work could be achieved within New Zealand. And in terms of how pump hydro work, I imagine most people realise it's fairly simple. You're just pumping water up from a lower reservoir to an upper reservoir, so that when you need the energy, you can then release that water back through your pump turbines. So the concept is simple, but it does have some requirements. Sorry, I'll just flip forward. And the efficiency of the plants is really related to the capital cost of constructing the plant, which is the cost of building reservoirs and tunnels and penstocks, and your powerhouse. So those costs are all really related to the amount of water that you've got to shift for the amount of energy that you can store. So you have an equation of head over length. So you want to maximise the height that you're pumping the water and minimise the length that you have to pump the water across or uphill or through. Now, there's a way of breaking down scheme types that I want to use into 4 different types of pump hydro schemes. One is to use existing reservoirs, so we just use a pair of water bodies and link those together through your penstocks. Another is to build a new upper reservoir above an existing one, and then a brownfields one, which might be using a quarry or existing infrastructures that you can use to build your pump hydro with. And then the last one is requires new upper and lower reservoirs. Scheme types 1 and 2 use existing water resources, so they inherently will interact with some existing morphological or hydrologic resource and alter that in some way. So that has some environmental constraints or impact around it additionally. 3 and 4 are what you can call closed loop schemes, so they don't necessarily impact on any existing hydrologic resource. However, they still will have environmental impacts because these are generally big projects. So you're talking constructing large reservoirs, and those reservoirs have large variations in water volume and therefore water level, and so you have a littoral zone around the outside that is continuously being exposed and flooded. So they're not necessarily useful recreationally either because of that, and they may have associated impacts with dust, etc. So if we have a look worldwide, what's been constructed, some of the projects are very, very large. Bath County is the biggest in the world, 3 gigawatts, 24 gigawatt hours, and its head to length ratio 0.22. Other ones can be very small. El Hierro is a very specific scheme built on a Canary Island, and it is built with a specific aim of ensuring that there's a 100% renewable power scheme on a very small island. So it only has an 11 megawatt capacity and a small storage volume. Other ones, high head schemes. So as I talked about, we want to be able to pump our water as high up as possible. So it's possible to have a scheme with a head of over 1,000 metres with Eldoro in Italy. But also schemes can have a low head, and what a low head might look like is in Kiev, where there is a scheme with a 70 metre head. But of course that's built to pump a large volume of water. In New Zealand, what is our opinion so far? There hasn't really been much. No one's really given a great deal of thought. But where they have is these sort of negative comments up the top are really what resound, is that it's seen as being prohibitively expensive, might be clearly stupid, difficult to contemplate, and no rational generator is going to look at it at the moment. High capital costs, environmentally and economically poor. And then, of course, even will the Greens, so even the people who you think should be invested in this type of technology and power system, might see it as having negative impacts. And summarise it, pump hydro doesn't make sense now. However, most of these comments are from a couple of years ago, and even in that time, our worldview has really changed in New Zealand in terms of carbon intensity, and we have comments like this skew perception is maybe due to the high projected cost of one particular scheme, the Manaburn Onslow, and we'll talk about that soon. And then conversely, pump hydro makes sense now. So we'll try to investigate more about what is actually what potential there actually might be in New Zealand. So to start off, we'll look at what's been proposed. The top one there is Lake Onslow. So that's been sort of investigated quite a lot by Earl Bardesley at Waikato, University of Waikato. He proposed a scheme to cover New Zealand's dry year shortage risks. So a very large storage volume, 12 terawatt hours, with a good high head, but you'll notice the head to length ratio there of 0.03 is quite low. So we've got to pump our water a long distance through the canals of penstocks in order to be able to store it. Mohammed Majid has recently just completed his PhD at Waikato and has released results filling out the actual scheme design there and giving it capacity of 1.3 gigawatts in a storage. But of course that head to length ratio for what he's calculated is more precise, but still very low. Another scheme that Majid has also looked at, as well as Bardesley, is the Wanaka-Hawea Pier. Those lakes are very close together through the neck, and they have a reasonable difference in head and elevation between them. However, there's all sorts of problems there with water use covenants on Lake Wanaka, which would make it infeasible, and the head to length ratio, even though those lakes are quite close together, is still very low. There's been vague other references to a Pukehi Tekapo scheme, and I can't work out whether or not that is also looking at using lakes Tekapo and Pukehi together, as has been mentioned by Barnett, or whether this is a separate thing referenced by the Productivity Commission. In terms of small-scale schemes, Ian Mason has suggested that this might be looked at for Stewart Island, where we have a very small, isolated energy system where diesel is being used, and it has very high costs of running it. A scheme could be constructed that does sort of pass this head-to-length ratio test. You can actually construct something which makes a sort of first-pass assessment. However, what's been looked at in New Zealand internally is not what we've only sort of recently been exposed to. So Australian National University has produced an atlas. Primarily they produced it for Australia, but being Australians, they like to expand and think we're part of Australia. And they've proposed that we should basically cover our entire country in pump hydro schemes using their very, very fancy GIS tool. I love it. It's, you should go and have a play with it. Look at the website. It's a fantastic interactive tool that you can look through, and it has some good stuff in it. I've found one scheme which is centre of the north, near Auckland up there. It's got a reasonable head to length ratio and would be potentially not a bad option, but then there's also some designs in there or proposed schemes in there that are patently stupid. So the bad there is actually using an upper reservoir up in the top of the Remarkables with a penstock that goes underneath Lake Wakatipu into another reservoir in the middle of the Eyre Mountains. And I'm quite familiar with the terrain, and that's just, yeah, it's nuts. There's not even a transmission grid particularly close. Yeah, so it's got good stuff and bad stuff, but what it does do is focus attention on the issue and presents a methodology for finding and designing schemes. So I've started doing this sort of a slightly more methodical assessment of what the potential in New Zealand might be. First of all, looking at type 1 reservoirs. So these are existing water bodies. It's a relatively easy task to sort through these. I can use the Land Information New Zealand water bodies data set, filtered that for Department of Conservation land. Otherwise, we end up with all of these possibilities in Fiordland. And I've also filtered out water bodies that are very small and only accepted those which have a head to length ratio greater than 0.06. So relatively flexible in that. And I get a list of quite a short list. And on the right-hand column, I start sort of analysing what the barriers to some of these schemes might be. So Wakatipu, Lake Johnson, although the head to length ratio is here small, I'll analyse this in a minute. Lake Luna, it's remote, it's very difficult to access. Lake Dispute, recreational area, Lagoon Creek again, it's very remote. A lot of these are remote. Anything around Lake Sumner, which is using Lake Mason, and then Loch Katrine, Lake Mason, is remote from the grid. It's too far out to realistically get a transmission infrastructure connection there. Then we have dams Avemore, Benmore, which has the same criteria, I suppose, or assessment. These are existing hydro dams on cascading rivers, is Karapiro and Arapuni. We've got an existing power scheme on the same river, which is potentially well utilised presently, and changing that into a pump store type scheme might be possible, but the benefit will impact on its present operation as well. And then there's Speargrass Creek, which is above Lake Roxburgh, and this is interesting because it uses the same water resource as the Lake Onslow scheme, so the same lower reservoir. So I'll look at that in a moment, but presently small storage. Again, Butcher's Dam is above Lake Roxburgh as well. The last pair there, Waikari Moana, Waikaraiti, we run into issues and have to start thinking of Kaitiakitanga. This is in Tūhoe land, and while it's not a national park, it's going to have some pretty stringent conservation criteria to have to assess if you wanted to be able to develop anything around there. So I'll look further at the Lake Wakatipu, Lake Johnson case. Lake Johnson lies just above Frankton. It's a funny little lake that I don't think many people really know about. I know the area pretty well. I grew up, my grandfather had a crib on the shore of Frankton Arm, somewhere about there, so I spent my childhood playing on a beach there somewhere, and I never knew about it. But Frankton is, well, Queenstown Basin is running some risks of not having enough transmission capacity, so there's an N-1 risk this winter that Transpower in Queenstown is going to be facing and thinking about. So having localised generation might have some benefit. There's another thing we have to think about in the South Island lakes, Lagos Siphon and other invasive aquatic weeds. But given all these barriers and forgetting about them, I've done some back of the cigarette pack calculation. Of course, that's not very popular nowadays. Cigarette packets are pretty ugly. But allowing some basic costing from the literature, we might be able to achieve a scheme for under $200 million, which equates to $330 per megawatt hour, or about the same per megawatt, and $293 per megawatt hour. So we can start doing some rough calculations, and from that start to work out what the value of balancing and the cost of balancing in the power system is. And I've been mentioning Lake Roxburgh a lot and Lake Onslow, and that's because Lake Roxburgh has a lot of options for it. We can look at a type 1 scheme, as I said before, with Speargrass Creek. So Speargrass Creek is to the east. It's not as far as Onslow on this map here. Onslow would be way down here somewhere, 20 kilometres away. So Speargrass Creek is quite a lot closer. But we can start thinking, well, Speargrass Creek, the volume of water that we can store within the dam as it is at the moment is very, very small. So we'd have to construct a much larger dam, in which case we're actually changing it into a type 2 scheme. Of course, I've got here the type 2 scheme of Onslow. We can also look and say, identify a type 3 scheme, brownfields, something which is already existing. And here I've identified an irrigation pond, which sits, the Roxburgh Dam itself is here, and as you drive up the hill over towards Alexandria, you go past an irrigation pond. The irrigation pond itself is not very big, but it does have a quite good head above the lake, and it's quite close. So we could look at expanding that irrigation pond, but then again, why not build a pond somewhere else, which is much better. And then type 4, this is where the ANU comes to the fore again. They actually want to, in their database, build a dam over the top of the Roxburgh Dam to act as a lower reservoir, and then construct a new reservoir in Speargrass Creek and 2. But that at least, confirms we're looking at the right places as well. But with all of these options for Lake Roxburgh, we go, well, what is the best option for Lake Roxburgh? We want to have an objective of what we're trying to do with this construction of this dam. Are we trying to cover dry year risk, or is there some other balancing function in the power system that we're trying to cover? We're going to look at the benefit cost of it, how much does it cost and what are those benefits? And then, since we're talking about best, we want optimization. We want to find what that best is through some optimization methodology. So objective, as I've said, with the power system, and we want to keep it balanced, and that requires keeping it balanced over temporal durations from seconds, because we've got to be able to cover faults and large changes in output of other generators. Diurnal, so if we're going to have lots of solar, we're going to have to vary our electricity output and keep it going through the evening peak. Synoptic, if we've got lots of wind power, then we find that the variability in wind generally progresses with the storms that cross New Zealand. And then, of course, there's that hydro dry year risk of supply. And within each of these, you're going to have some way of financing or paying for your service provision storage. And pump storage plants overseas generally don't earn all of their income from only arbitrage. They also have to provide ancillary services and also procure some income through security supply provisions. And in terms of our objective as well, we've got a topographic resource here. So we could put our new reservoir anywhere, but we'd have to build it in some way with a dam or a ring dike. And we've got topography around Lake Roxburgh and a lot of it. But we've got constraints with the lake levels and the discharges and spills, and other things we have to consider as well as the transmission capacity and where the connection is going to be, how long our transmission lines are going to need to be, the access, because we can't just build a dam in the middle of absolutely nowhere. We've got to get to it to do it. And also our powerhouse. We can't just construct that absolutely anywhere. It's got to be feasible. The land ownership, of course, comes into it as well, because you're going to have to convince whoever owns that land that you're going to be able to use it. And then other elements, kaitiaki tamia again, you've got to establish relationships with local iwi and other members in society to ensure that what you're doing is acceptable on a wider level. So in terms of the benefit cost for what I've done, this is what I'm starting to show. I've built a model to be able to optimise the location and look for an optimal location for this upper reservoir. The benefit, as I sort of mentioned in the previous slide, it's a really, really complicated relationship. And I've just modelled that as a log function of the volume of storage divided by the capacity, just as a proxy for doing something. If you don't do that, you have a linear, you're just going to flood everything. Otherwise, if it's the other way, you're going to end up with this really silly small dam. You've got to have something which works. The cost model, I've gone to a reasonable effort to build a model for a dam, a rock core earthfill dam. Penstocks, I've got some figures out of the literature for the cost of building tunnels, which can assume that the ground will need support. Powerhouse, there's reasonable models in the literature for the cost of a powerhouse given the volume of water that's moving through it. And then built into the model as well, I've got a model for the cost of the land. So there is a cost of land in there. However, I haven't put asset values in it, which will come to the fore later. The way in which I've enabled my algorithm to work is I've used assumed a polygon on, in this case, a rectangle is laid across the land, as you can see in the graph here, and then that is intersecting a contour, and then the algorithm will calculate the flooded area, flooded volume, upstream from where a dam is going to be built across here. And then I've put that inside a particle swarm optimization. So for each iteration, each considered location, I place my polygon with a flooded depth and a radius and allow 5 degrees of freedom, so easting and northing, the radius, the stretch of the rectangle, and then the flooded depth. And so the algorithm calculates what the cost of a scheme would be given the polygon placed in that particular place on the map. I've assumed a 200 megawatt power plant, and then embedded this within a genetic algorithm. And this sort of funny video here will show you, start off with the points all placed across the map within a region that is meeting a criteria of head over length is greater than 0.1, and then run it to converge. It's a rather complicated thing, but I'll rerun the video. You can see that it starts out with all of the particles spread across the landscape. The green is a good solution, the red is a poor solution. So you can see the poor solutions are up high on this very rugged topography. The green solutions are at the start located across flatter land with a higher head. And then as the algorithm progresses, they quickly find that one location in the centre there and start turning green. I have a very, very simple optimization at the moment where I've really just used basic default parameters for guiding it, and that's why it gets into this sort of jiggly pattern at the end where it's not really optimizing any further. I haven't got any damping in the iterations or anything, so there's a lot of work to go on there. But nonetheless, the algorithm does converge on a solution. I've tested it fairly extensively and it's pretty rigorous at finding this option, which is it floods Fruitlands, which is halfway up above the Roxburgh Gorge. And as I've said, it's a quasi-optimal solution, so a genetic algorithm doesn't pretend to be able to find the actual optimal solution, but the best out of the space that it has looked through. The initialization is constrained, but the actual algorithm itself is not. In terms of this option, we would have a powerhouse deep in the Roxburgh Gorge, which would be pretty difficult to construct, but maybe not impossible. We also have to start thinking about the geotech, how much is it going to cost to build this in fractured schist. And through this, we actually have an inactive fault. The Fruitlands fault passes through this particular location. Of course, that may not be an impediment. The Clyde Dam is built on an active fault. So we have to have appropriate engineering design and risk assessment undertaken. I also haven't, as I said, got the land values correctly or entirely put into the model. So it's flooding the main road, State Highway 8, goes through there, and it's also flooding some 33 kV lines. 110s go through the other side. And also, there's potentially some sites of interest in there. This is an old gold mining area, so there's going to be some archaeological values in there. But nonetheless, we can see that the head length of this option would be 0.15, so better maybe than the Onslow proposal, depending on what the objective they're trying to achieve is. 8.2 gigawatt hours of storage, so much, much smaller than the Onslow, but come out with a cost of $228 million. Of course, that's a real back of the envelope calculation, and real costs and real projects differ from those quite substantially. So I'll move on from that sort of best option type 3 to have a look at some type 3 schemes around the country that we might be able to have a look at. These are brownfield sites, so we're looking for areas that have already been developed. And Australia has a proliferation of mines all over the place. They have big holes in the ground, and quite a few of those are being turned into pump hydro schemes, and in New Zealand we don't. But we do have one option, which is McRae's, although it's still active, but once they're finished getting gold out of there, maybe we could use those pits quite usefully with a good head-to-length ratio, and it's got a 66 kV line right there, so that could well have some value to Oceania Gold. Other ones we have in New Zealand, we have irrigation schemes, and I've identified 2 high-head irrigation schemes, one above Lake Dunstan, so both of the at Dairy Creek, which is owned by Pioneer, and although the capacity is small, the head not very high, it may be possible. And again, a slightly better option would be the Hakataramea irrigation scheme, which takes water just downstream from Lake Waitaki on the Waitaki River. And here we might be able to have some synergies as well. So the irrigation demand is in summer, but our demand for storing energy and balancing energy is likely to be greater in winter. So we might be able to couple these schemes and have some synergies with other industries to spread the costs. Move on to type 4 schemes. Now this starts being a really complicated problem, because although with type 2 there's a huge number of options, I looked at one, Lake Roxburgh, but other options for type 2 schemes would obviously be looking at is more likely above the Waikato River. All those dams down the Waikato have quite large levees on either side. Whereas type 4, we don't have to be constricted to where there are existing rivers. So we can look anywhere. And in New Zealand, or anywhere where there is a big hill that we can build a dam on top of and a dam at the bottom of. And in New Zealand, that still encompasses a large number of options. So I've run my little particle swarm optimizer, modifying it so it's even more complicated. So it looks for constructing a lower reservoir and an upper reservoir at the same time, and the degrees of freedom end up expanding horrendously, so you end up with 10-dimensional problem, which probably possibly is getting beyond the limits of what you should really be using a particle swarm type optimization tool for, but there needs to be a lot of development work and optimization tools for this type of problem. So what I've done here is I've picked out the Ruakawa range, which is in the southern Hawke's Bay, just to sort of demonstrate the use of the tool and what we might be looking to achieve. I've, by eye, spent a bit of time looking over this and going, oh, where would I put a couple of reservoirs? And decided that this blue one here and this dark blue and the cyan reservoir up here might be a good best guess. I've then run my particle swarm optimizer. These blue dots linked with the lines are the initialization pairs, and then those have converged to give my output from my PSO, which is this yellow and this green reservoirs. So the PSO seems to be doing the right thing. It converges to what, or near to, and betters what might be a best guess in this case. But as I say, the problem itself is very, very huge, and actually looking for specific resources in New Zealand is going to be a very big problem, and whether or not an optimisation algorithm like this really is the best approach is to be explored. So the future direction in terms of the research and assessing what the potential for pump storage will be in New Zealand, something I think needs to be done, especially if we want to actually work out what the cost of achieving a carbon neutral electricity system is. We're going to have to start defining those requirements for storage, what those dry year issues are, and what quantity of storage and where we want it. Then start looking for those type 2 schemes and assessing those. As I mentioned before, the Waikato River would be a pretty prime example. And then a type 4 search, start looking at the costs of type 4 schemes, again, where those should be, probably near Auckland, as that's the main load centre. For what I've done, there's a lot of work that can be improved upon, delving into the geotechnical element of it, which is very, very difficult, and there's not a lot of information actually on the geology of the strata subsoil, and well, building some relationships and working with people on that, and then looking at the morphological resources. I don't actually have any, I haven't implemented a cost for spillways and auxiliary components for the schemes that will be needed into my model. The accurate road model as well, put in some roads into it, and transmission is my type 2 search for Roxburgh showed, flooded a road and took out some power lines. Assessing the cost of that littoral zone, so actually putting a cost in there for the impact, the environmental impacts, and those are all taken through the strange thing, the RAM, which is the Water Resources Assessment Methodology, which is just a way of assessing the environmental impact of what you're doing. In terms of the optimisation itself, I've just, as I said, got a very straightforward particle swarm optimizer. It needs tuning, but it also needs to start looking at swarm clustering. And then there's sort of novel techniques in this field of optimisation that are developing all the time. The blind bulldozer ant algorithm sounds really cool, which would be literally where you let loose a ton of bulldozers in a place that you want to excavate and just let them go, which is not a silly idea because the geotechnical risk in these projects is really huge and you don't know what it is before you start digging in the ground. So actually just having some autonomous robot bulldozers going around might be a solution. So in summary, in terms of the pump hydro for New Zealand, the potential of it, it's a mature technology. It has the lowest CO2 intensity, the best energy stored and invested. It has circular economic benefits, so I think it's really something we should be looking at, but it's economies of scale and whether or not an individual power company could take on the full risk of financing it would be pretty sort of courageous of the individual company to do, and I'm not sure whether they would. There's been little investigation to date, it's focused in New Zealand, but there is good scope for projects using both the existing and new reservoirs. But yeah, capital intensive projects, complex risks, so we need careful planning. The other thing is that the schemes take a very long time to build, construct and design, and so the lead time is very long, so we need to really start looking now if we want to be constructing things by 2030 and having them working. And then I've sort of outlined the development of an automated search and design tool and sort of shown where I think that should go. So I thank the Green Group for sponsoring my work here. And most of the sponsors as well. Much.